Hello friends, welcome to today's discussion. We are going to discuss one of the most fundamental and most important topics in all of science. It's about quantum electrodynamics. Quantum electrodynamics describes how fundamental particles interact among themselves and how the four fundamental forces act. Let's see. Feynman diagrams. Richard Feynman discovered this Feynman diagram to simplify the concept of interactions of particles. How particles interact among themselves. We want to understand it in a simple way, in a graphical or in a geometrical way. He really simplified this, one of the most tough topics. So here, do two electrons interact among themselves to create a gamma photon and then annihilate and gamma is produced, and they also created themselves again. In this diagram, time flows in this direction and space in this direction. So these are vortices and propagators to represent the interaction of this fundamental particle. So there are some conventions for drawing Feynman diagrams. For fermions, so spin-half particles, such as electrons and other fundamental particles, we use simple line to represent the interaction, and this arrow represents the flow of time. For particle, this arrow is in this direction. For antiparticle, the antiparticle will flow in opposite direction to this arrow. So this arrow follows the direction of particle flow. And photon, we represent the flow of photon in this wavy line, and the cross section, when two lines cross each other, we tell them as vertex. So these are vertices. These vertices and propagators together combined to represent the interaction of this particle. So Feynman diagram consists of lines representing particles and vertices, which particles are created or annihilated. Feynman diagrams are combination of vertices. Vertices are places where particles are created or annihilated. In this case, the electromagnetic interactions, there is only one way, the one basic vertex which couples a photon to a charged particle with strength proportional to its charge. Each vertex has an arrowhead, okay, pointing towards the vertex and an arrowhead leaving it. Okay, one vertex represents the pointing, it will point where the particle is flowing, and an arrowhead it will leave. This represents a same generation lepton transition or same or neighboring generation of quark transition. The arrowheads are drawn in the lines rather than at the end of them. Arrowheads you are drawing on these lines, you can draw in the middle, not in the end of the line, to represent the flow. At each vertex conserve energy, momentum, angular momentum, and lepton numbers. Lepton number for electron is 1 plus 1, and electron neutrino and other positron anti-electron neutrino, that is -1. Similarly, lepton number of muon and tyon, and this also conserve baryon, strangeness, parity, It's also conserved, but except weak interaction. Weak interactions you can't say these all are conserved. So these are Feynman diagrams. We can draw many Feynman diagrams for a single interactions, but we have to draw the simplest one, okay, to understand the concept easily. Here one gamma photon is decayed into positron and electron. Here one anti-muon and muon. Here gamma ray photon decay into tyon and anti-tyon, like this. Up quark and down quarks, strange quarks, these are all particles. Lines. The lines represent the quarks or leptons are straight lines or solid lines. These lines represents the exchange of particles, okay, that wavy in the case of photons. In case of photons we make the line as wavy. For W and Z bosons they are also wavy, but for gluons it is curly. Some authors use broken straight lines to represent W and Z bosons, okay, which is it is not international. It is not these conventions, this lines we are representing is not international. You can use your own way, but it is the simplest one. The common use of the same wavy line to represent both the weak interaction of particles and photons reflect the fact that the theories of electromagnetic interactions and the weak interactions have now been combined into electroweak theory. Electromagnetic theory and the weak interaction are combined together to form a single theory, a unified theory of electroweak interaction, okay. We always try to combine the most fundamental theories to unify them, and many have already unified, but many have to. Spin-half quarks and leptons, representation of these particles in the Feynman diagrams. We can represent the spin-half particles like quarks and leptons in this fashion, in a straight line. For spin 1 particles like gamma, the quantum particles of the interactions or the Gauss bosons, gamma, W plus minus, and Z bosons, and gluon. For gamma and W and Z, we represent it as wavy line. For gluon we represent it as a curly line. You may have known that the particles which are made up of quarks, there are two types of particles which are made up of quarks. The particles which have half integral spin, we call them as baryon, and the particles which have integral spin we call them mesons. These baryons and mesons are classified as hadrons, okay. And then the particles which are not made up of quarks but have half integral spins, they are leptons, like electron, tau, muon, etc., etc. And there are some quantum particles of forces like gamma photon and W and Z bosons, and gluon, they are Gauss bosons. There is another boson, scalar boson, which is Higgs boson. The direction of time in this Feynman diagram. The diagram shows time flow with time going from left to right or from top to bottom as you wish to represent. So arrows drawn in the same direction as the increasing time direction represent particles traveling forward in time. If arrow represents in the same direction as increasing time direction, then particles are going forward. And in case of antiparticles, it will be reversed. So arrow drawn against the time direction represents antiparticles traveling forward in time. And particle levels, we have created some particle levels to simplify the game here. So particle levels such as electrons, up, down, these are quarks. There are also some strange and all sort of quarks. These are funny names actually, and are placed outside the diagram at the end of the arrow lines. The levels represent free particles approaching or leaving a reaction. These levels, okay. If the arrowhead points backwards in time, then the free particle must be an antiparticle, okay, and be labeled as such. You have to label antiparticle with the opposite. You can use it like plus minus sign to represent antiparticles or particles, okay. Exchange particles link vertices. How exchange of particles takes place in the Feynman diagram. Exchange of particles have to link to a vertex. The cross of these lines, curly or wavy or simple straight lines, who have to have vertex at the interaction point. Arrowheads are not normally drawn on exchange particle lines. Okay, on exchange particle lines, arrowheads are not drawn, okay. The direction of the exchange particles flow in is indicated by the line's orientation on the diagram. The line is labeled with the symbol for the exchange particle being drawn alongside the lines. The Feynman diagram is a pictorial representation of a matrix element describing particles decay or interaction. We represent it to describe a decay or interaction of fundamental particles. Like A becomes B, A decays to B plus C or ... or any other, etc. Okay, and A plus B, A and B decays to C and D. So rules to draw Feynman diagrams and determine whether the process is allowed or not. These are the rules. First is what it says: write down the initial and final state of the particles and antiparticles. Initial state, and note down their quark contents in case of hadrons. Okay, in case of hadrons you have to note down the quark contents and draw the simplest Feynman diagram using standard model of particles physics and their interactions in vertices. Yeah, that is the simplest Feynman diagram you have to draw. There are infinite number of Feynman diagrams are possible for single interactions. Okay, keep in mind. So similar diagrams for particles and then antiparticles. Okay, and never have a vertex connecting a lepton to a quark. Never connect them. Never connect lepton to a quark to a vertex. Only the weak interactions vertex changes flavor. Flavor, what are the flavors? Up down, left or up down strange charm, like that. And but color may change. Color surges in case of gluons, they may change. If all particles or all antiparticles, these are the scattering diagrams for becoming A, B decays into C and D. Initial state A and B and becomes annihilated through gamma and become gamma ray photon. Then also they created C and D. This is the final state. The particles and antiparticles may be able to have scattering or annihilation diagrams. And T channel and the Mandelstam variables are used. T or S channels A and B annihilated and produced gamma ray photon, and they created C to C particles. And here also time flows in this direction here, but here time flows in this direction as the arrow points in this direction. Okay, so here to B and B and D decays on and highlighted to produce gamma ray photon, and then they created A and C particles. Molar scattering. These are molar scattering. Here two electrons annihilated and produced gamma ray photon, and then they created themselves back. Here two electrons enter, a photon passes between them, and the two then exit. This diagram then describes the interaction between two electrons. In a classical theory, it is the Coulomb's repulsion of the slack charges. In classical theory of the electromagnetism, if the two are at rest. In quantum electrodynamics, simply QED, this process is called molar scattering. Okay, and quantum electrodynamics, the interaction is mediated by the exchange of photon. An exchange of photon is used, mediated, to represent this interaction. It is the molar scattering. You can draw the Feynman diagram in this way. Time flows in this direction. Molar scattering represents the flow of particles in this direction, and there are electron and positron pair is created in the middle, in the smallest portion of the middle portion of the space and time. They have created and annihilated, then they also created again two electrons. Time flows in this direction. Two electrons interacted, and there is a gamma ray photon. There is a gamma ray photon is produced by their annihilation, and then they created themselves again. One can twist these Feynman diagrams and around into any topological configuration. You can produce any configuration. Okay. As per the convention, a particle line running backward in time, as indicated by the arrow, is to be interpreted as the corresponding antiparticle going forward. The photon is its own particle, own antiparticle. In this process, an electron and a positron annihilate to form a photon. Okay, in the previous example, previous diagram, which in turn produces a new electron-positron pair. An electron and a positron went in, an electron and a positron came out. Okay, through annihilation and pair creation. This represents the interaction of two opposite charges, the Coulomb attraction. In quantum electrodynamics, QED, this process is called Favre scattering. Okay, Favre scattering represents by these Feynman diagrams. Favre scattering is the electron-positron scattering process. You can see two electron and one electron and one positron annihilated and produces gamma ray photon, and then they created themselves back. And you can also also draw the Feynman diagram in this way. One electron is going in this way, and then exchange with gamma ray photon, then they created an electron. Okay, and then this electron goes in this way. So you can represent in this way also. The Favre scattering, you can draw the Favre scattering Feynman diagram in many ways. You can see here. Yes, you can draw in this way. Electron positron is created in the small space and time, and they also annihilated, and then they also created themselves. These are all Favre scattering. You can see how many Feynman diagrams it can be drawn for the same interaction. Okay, pair annihilation, dark matter creation from annihilation. They can see electron position is annihilated and created dark matter pair production. Two photons interacted with themselves to create electron and positron. You can represent Compton scattering, explain the Compton scattering in this through these Feynman diagrams. An electron enters in this way and emits a gamma photon here, and then continues further with the electron. It creates an electron and then it continues in this direction in time, then absorbs this gamma photon from nature. Okay, then electron continues in its own path. Okay, it goes on. Here electron positron attraction, here electron positron annihilation, electron positron pair production, and Compton scattering. All the Feynman diagrams in one place for these fundamental interactions. Okay, and then we have to move to quantum chromodynamics. What is quantum chromodynamics? Quantum chromodynamics represents the fundamental interaction between the quarks. It is strongest. It represents explains the strong force of nature, and exchange of gluons between quarks is the most strongest force in nature. In quantum chromodynamics, the force between the two quarks is mediated by the exchange of gluons. In quantum electrodynamics, on the other hand, there is only one kind of electric charge. It may be positive or negative, but a single number is sufficient to characterize the charge of a particle. Okay, but in quantum chromodynamics, there are three kinds of colors like red, green, and blue. You can represent the charges by these three colors: red, blue, and green. So in the process Q, quark, Z, these colors of the quark may sense in the interactions. These color charge of the quark may sense, but flavor, the up down some sense, they not sensed. Okay, you can see in this Feynman diagram one half quark, which is blue in color, goes in this direction, and gluon interacted with a gluon which is not bicolored, because the gluon have to have both the colors. To conserve the color, we have to make it negative and positive. Blue is positive and red color is negative, and red color is red color up quark is produced again in this interaction. So gluons are, for example, a blue up quark may convert into a red up quark in this process. So since color like charge is always conserved, this means that the gluon must carry away the difference in this instance. So 1 unit of blueness and minus 1 unit of redness. Okay, gluon then are bicolored, carrying 1 positive unit of color and 1 negative unit of color, bicolor charge. Since we have 3 different sorts of quarks, red, green, and blue, to connect them all together we need 3 cross 3, so 9 different gluons. But we need coupling quark is not coupling is 0 here, so we need only 8 gluons. You can see in this interaction particle flow. In this interaction, red quark is going in this way, interacted with red B dash. B dash means negative blue, and created a blue quark. And in this diagram, you can see the color flow. Red flow in this way, red and blue is flowing in this direction. In this same interaction, you can also represent by color flow. Okay. And since we are connecting together quarks or different colors, yes, so gluons must colored too. Gluons have colors. Okay, so the possible gluons RB dash, RG dash, GR dash, GB dash, BR dash, BG dash. Plus 3 orthogonal combinations like RR dash, GG dash, and BB dash. Okay, these are orthogonal combinations also allowed, but coupling is not allowed in quantum chromodynamics. Only 8 gluons is possible. Since the gluons themselves carry color, they couple directly to other gluons. Okay, and hence in addition to fundamental quark gluon vertex, we have primitive gluon vertex, gluon vertex, like these are gluon vertex, but there are 2 kinds, like 3 gluon vertices. This is 3 gluon vertices and 4 gluon vertices. Okay. Comparison between quantum electrodynamics and quantum chromodynamics. What are these comparisons? Let's see. Quantum electrodynamics mediated by massless and spin 1 bosons like photons coupling to conserve electric charge. Here electric charge is conserved. So in quantum chromodynamics mediated by massless spin 1 bosons like gluons coupling to conserve color charges. Okay, this is the first difference. So quantum electrodynamics, there is only one kind of electric charge. Okay, it can be positive or negative, but a single number is sufficient to characterize the charge of a particle. Yeah, okay. And for quantum chromodynamics, up down strains, some strains, all these charges have same three colors, like same colors, red, green and blue. So identical strong interaction. So identical strong interactions of particles. Then leptons are colorless, so don't feel strong force. Remember, this is an important point. Leptons can't interact with gluons because they are colorless. Okay, they don't have color charges. That is the point. Okay. So fine structure constant, it is really important in the quantum electrodynamics, quantum chromodynamics, and Arnold Sommerfeld introduced fine structure concept in physics in 1920s. Okay, to represent the atomic splitting lines, atomic spectral lines. Over the years, the fine structure constant alpha was discovered to be fairly universal constant, appearing everywhere in the particle physics, quantum electrodynamics. The fine structure constant measures the strength of electromagnetic force, and that controls how such elementary particles such as electrons and photons interacts. Okay, how they interact and the strength of the electromagnetic force is all described by this fine structure constant. We call it alpha. The fine structure constant alpha describes how electromagnetic radiation affects such particles. Yes, so it has measured numerical values. It is 0.007297351. This is really very precise result, up to 6 decimal place. The uncertainty of 6 in the 6 decimal place, and such one of the best measured numbers in all of physics, not in only physics, all of science. Okay. It is a fundamental physical constant characterizing the strength of the electromagnetic interaction between elementary charged particles. In quantum electrodynamics, the coupling of the fine structure constant is alpha equal to, we can calculate the value of fine structure constant in this fashion, like 1 by 4 pi epsilon naught into a square by a cut c. We will get 1 by 137. You can get the value of 0.00729927007299227. So it is one of the most precise value in all physics, not in only in physics, all of science. Okay, all of science, not in only in physics. Okay, so it is a shielding effect of charges. You can see at the large distances, don't see full charge. Okay, they have dipole moment, dipole charges, but this middle charge is shielded with these dipoles. And in small distances you can see only the single charge. This is alpha versus q square value, that is 90 GeV square, and you can see it is increasing exponentially. You can see it is increasing exponential increase. Okay, each vertices in quantum electrodynamics introduces a factor of alpha. Okay, and the smallness of this number means that we need to consider Feynman diagrams with small number of vertices. If we need smallness of this number, then we have to make Feynman diagrams with smallest possible vertices. Experimentally, the corresponding coupling constant for strong forces, that is alpha s, as determined from the force between two protons, is greater than 1. Yes, and the bigness of this number is compared to quantum electrodynamics was a real problem. Asymptotic freedom. In quantum chromodynamics, the coupling constant is in fact not constant at all, but depends on the separation distance between the interacting particles, and it is called the running coupling constant. The experiment shows that the forces containing the quarks get weaker and as the quarks get closer together. Okay, and we can see they will have some freedom to move without interaction, so that within the confined baryon or hadron they are essentially free to move about. The condition is referred to as asymptotic freedom. This asymptotic freedom means that within a proton or a pion, the quarks can move around without interacting with themselves. Okay, at low energies, quantum chromodynamics becomes strong enough to confine quark inside hadrons. They can confine them. They can confine quarks at low energies. At high energies, quantum chromodynamics is asymptotically free. They have no interactions, almost no interactions with themselves. This is a curve between strength of the interaction of a running coupling constant of quantum chromodynamics, strength of the interaction between and distance. So you can see the strength is increasing exponentially, and this is the radius of proton. Okay, this is this point. You can see it is the radius of proton. One more difference between quantum electrodynamics and quantum chromodynamics is that many particles carry electric charge, but necessarily occurring particles carry but no necessarily occurring particles carry color. So this the color charge is actually we have made up to ease out to simplify the business, to understand quantum chromodynamics. Okay, experimentally it seems that quarks are confined in colorless packages of 2 mesons and 3 baryons. For example, the strong force between two proton-proton interaction, we have strong force between 2 protons involves among many others the following diagram. This is the up quark and up quark interacting with themselves, getting and highlighting, and they creating a pion. Then they created themselves back. You can see in this diagram. This is a beautiful representation of a nuclear force, how neutron and proton are made up of, and how they are interacting through color charges. You can see red, blue and green colors, and they are interacting and creating themselves back and up down quarks. It is a really interesting diagram. So as if quark confinement, how quarks are confined. So as if if you want to pull up a up quark from the proton, a pair of quark is created again in them in the inside of a proton. So instead of the free quark, we are left with a pion and a neutron. Okay, so thank you so much for joining in this discussion. So looking forward to see you again in the other discussions. Okay, bye.